Okay, we're in section 10.4, and this will be split into sections A and B. A will look at digital applications, and B will look at analog applications. And we're going to limit ourselves to just looking at the applications within this particular chapter. Entire books have been written on transistor applications because there are just so many of them. So we're just going to be looking at just a small sampling of things that can be done with transistors. First of all, digital applications. When a transistor is used as a switch, it is either fully on or fully off. Transistor switches are common in digital circuits, industrial control circuits, burglar alarms, computer circuits, and many more. A transistor switch used as a lamp driver is illustrated at the right. So here we have a computer, and it's connected to a transistor and to a light. Recall that the transistor as a switch is either fully on or fully off, and so this would correspond to saturation and cutoff. Those are the terms that are used to describe that. And cutoff, there's no current. Saturation, it is maximum. So the industrial computer, the outputs would be, with the computer you're just going to have two levels of outputs, and typically the logic levels would be 0 and 5, 0 for a low and 5 volts for a high. Now if there is 0 volts going to this configuration, then the biasing from the emitter to base junction is going to be 0 and 0. And so if there's 0 volts across this diode, we don't have any current flow. And so if there's no current in the emitter, there's no current in the collector, and this looks like an open switch. And if we were to measure the voltage here, you would see 24 volts. And I'll make that, I don't want to confuse, I think that is negative. But the transistor in this case essentially looks like an open switch because there is no voltage drop. Well, there's a voltage drop across it, but it's just the supply voltage here, and this is not conducting, and there is no voltage across the light, so it is off. Now, if we have a 5 volt input coming out of our computer, it'll first see this base resistor here, and it'll see the resistance of the diode. Now the diode will drop 0.7, and this would drop 4.3 of that 5 volt if it's a 5 volt input. Now what would happen in this case is that now we have the proper biasing. The diode is going to turn on, and this diode is going to conduct in what we call saturation. It's going to conduct as hard as it possibly can, and the biasing on the base, the collector, it will also go into saturation. And usually what you'll see here, remember we've got 0 here, we see 0.7 here. Recall that this is just another diode here. Okay, this is just another diode, and it's going to saturate. It's going to conduct as hard as it can, and so and if there's 0.7 here, then this is going to reach towards 0. Now what you'll usually see is maybe 0.1 to maybe 0.2 volts here. And so now we have a situation where if we measure the voltage from here to here, we would be seeing maybe 0.2 volts. It would be, and this would look like almost like a dead short. Now, the result of that, if there's only 0.2 volts here, that means that there'd be about 23.8 volts across this light, and so the light would illuminate. One of the advantages of using a transistor in this configuration is that we have this industrial computer. The computer is not going to put out much current, and so remember that the current that flows through the transistor is a function of what we call beta. Well, actually, the relationship of the current between the collector and the base. And remember that beta varies greatly, and beta could be, I'll just throw a number here, it could be 300. So that would mean that the collector current would be 300 times greater than the base current. Remember that we said that when current flows through the emitter, for practical purposes, we say that IE equals IC because such a tiny amount of that actually goes through the base. So if we had, say we had, I don't know, 1 amp of current flowing from emitter to base, then if the beta was 300, then the current that would load this computer would be 1 amp divided by 300, which would be, down in the, it would be very small. So that is another reason why a transistor is used as the interface, because it simply will not load down the source that's telling it to turn on. Okay, integrated logic circuits. All modern computers are built around integrated circuits, i.e. ICs. ICs are made from tens, thousands, and even millions of integrated transistors. The pins on an IC connect to some of the interface transistors. Bipolar. Modern ICs do not use the bipolar transistor as often as in the past, but their functions are still applicable. In fact, very frequently they're using the MOS technologies. Okay, input circuit. And here we have an input circuit. This circuit uses a PNP, common collector transistor, and Schottky diodes. And so this could be an input into a digital circuit. And we're using a Schottky diode here. What this is going to do is it's going to protect the input over here from high voltage. If the voltage is too high, it will short to ground through the Schottky diode. D2 is a collector clamping diode. It keeps Q1 from going too deep into saturation. This allows the circuit to switch from saturation to cutoff more rapidly. And what they found in transistors is if they go into saturation too deeply, it takes them a while to get out of saturation and into cutoff. So this diode will keep that transistor from going too deep into saturation. And the output will come out here, and the output will be either a high or a low based on cutoff or saturation. And again, in this particular situation, if the transistor is cut off, then the full 5 volts would be felt right here. If the transistor is saturated, the voltage from here to here will probably be about 0.2 volts, and so the output would be about 0.2 right here, because if there's 0.2 from here to here, then you would have your output right there. So the outputs in this would be probably about 0.2 and 5 volts. This would be the low. This would be the high. Okay, then we have a totem pole output circuit. This totem pole logic provides either a high or a low output. If T3 is on, T4 is off, and vice versa. And so here we have this unique configuration, and the idea here is that one transistor will be on, the other is off. And when that occurs, the transistor that's on, remember we looked at saturation, if this one is on, we'd have only about 0.2 volts across it, and then if this is a 5 volt logic, then the remainder of the voltage would be down here. And so if this is going to ground right here, then that would give us our high. Now, if the reverse situation, if this were conducting, we'd have about 0.2 volts here, and this would be open. Most of our voltage would be dropped here. There'd be about 0.2 volts here, and that would represent our low. And so this is a totem pole output circuit frequently used in the output stage of digital circuits. Then we have the MOSFET, and this is a CMOS inverter. MOSFETs are used in the majority of ICs produced today for digital products. Both P and N channel devices are commonly used, and if you look at this, here we have an input, here we have an output. This is an N-type CMOS, and this is a P-type. And what we'll see, 0 volts in will cause Q2 to be cut off and Q1 to saturate. So we have a 0 volt. If you have 0 volts coming in, Q2 will be cut off and this one will saturate. Now, with these E-mode MOSFETs, it will have the same phenomenon. When this one is cut off, it's going to represent an absolutely giant resistance. And when this one is cut off, it's going to look like a short. And with CMOS, the resistance is so large here, and the short is such a small drop here that to a fairly close approximation, the outputs are going to be either 0 or 5 volts. And okay, and the other extreme, 5 volts in will cause Q2 to saturate, so this would be shorted, and Q1 to be cut off. Now this is the same idea as the totem pole logic. One is on and the other is off. The transfer curve in your text shows the crossover points are about 2.5 volts. So you have your input coming in probably 0 and 5 volts, or 0 and 3.5, or depending on the digital logic level. And with the crossover points are about 2.5 volts. Now your text doesn't mention this, but CMOS technology makes very low current devices possible, and things like digital watches, satellites use CMOS technology because they need to operate on extremely low currents. You may have observed with a digital watch that the battery seems to last forever, and that's because it is built with CMOS technology that operates on extremely low current. Then there are hybrids. Bipolar technologies are generally faster than MOSFET technology, but consume substantially more power. So the bipolars are faster, but they use a lot of power. The MOSFETs are very low current. Bipolar devices also drive greater loads at higher speeds than MOSFETs. Okay, so bipolar is more suitable for higher loads. MOSFET devices can be built with higher densities. So manufacturers often combine the two technologies within an IC. So within a given IC, the MOSFETs, you're able to put a lot of them on a chip. You can pack them at higher densities than you can with bipolar. And so manufacturers like Intel will often have what they call a hybrid, which will be combinations of MOSFET technology and bipolar in their digital technologies. Okay, memory devices. All computers make extensive use of semiconductor memories. Transistors, bipolar, and MOSFET are used as memory elements. MOSFET memory is the more common. Each bit of binary data is represented by a cutoff or saturated MOSFET. So that's notice that every bit of memory data is represented by either a cutoff or a saturated MOSFET. So the MOSFET, you'd have 8 tiny MOSFETs to represent 1 byte of data. Also, MOSFETs or memory devices using bipolar and MOSFET. When you look on a computer and you see the cache, the L1 and L2 are built out of this type of device, and this is part usually built right into the microprocessor. So you'll see this in memory in your PC. Okay, so this has just been a really brief look at some of the applications for transistors, and we looked at memory, we've looked at hybrid, MOSFETs, CMOS, totem pole output, we've looked at integrated logic circuits, and okay, that concludes our look at digital applications. In the next section, we're going to be looking at linear applications for transistors.